All right, so just to reiterate, just quickly, we had and you want to do this in the order. You want to look at the number of peaks, and the reason was because that tells you the number of chemically non-equivalent hydrogens there are, like how many different environments you can find those hydrogens. Then you want to compare the integration, and that's because that tells you the number of hydrogens that are equivalent to each other in that particular type of environment. And then the next is called the multiplicity. It's also referred to as splitting, and it'll be obvious in just a moment the reason why. And so if I use the term singlet, because right there if you see it says that not all peaks are singlets. What is a singlet? Well, I mean, it just means a single, like a single peak, you know. So if the way that we've been drawing, or I have drawn the TMS, that's the 0 point. The TMS is a singlet. It's a single peak, and that's because all of the hydrogens on that, all 12 of them, are perfectly identical, okay? And they're all perfectly identical. So that's why we have one peak and it's a singlet, because we're going to find out that there's no splitting that can occur there. And then let's go to 10. We have the little delta, lowercase delta, ppm. This is for the proton NMR. But when we say splitting, what would happen is there are times that you would see something that looks like this. Okay, where it looks like there are 3 peaks to it, but that's actually considered one peak, but it's called a triplet, okay? And that tells you something else. That's the multiplicity, that's the splitting. And the nuts and bolts to it, like if we're going to do the cheat sheet, is it gives you an idea of the number of hydrogens that are on adjacent carbons. Okay, so this is the part that actually helps you put it together like a jigsaw puzzle. Okay, the number of peaks tells you the number of hydrogens, integrin lets you know the total number of pieces that you have, and then the multiplicity actually helps you to put it all together, like what piece goes in each location. In just a moment. Okay, so if we looked at this, this is actually, I would expect you to be able to name this one. This is, 1,1-dichloroethane. And so they're not showing the TMS. So if I were doing this, just get white, I would expect you can barely, I mean, if you look close enough, there's a little tiny blurb right there at the 0, but we would just draw in that, and I would say, we would write in, TMS, there's where the TMS would be, because that's your reference point. Okay, and then they've color-coded this to let you know. At this point, I would expect you wouldn't have known how to do the splitting, but I would expect that you would have known that there should be 2 different peaks, because we have a CH3 group and the CH. The CH should be further downfield for 2 reasons. What's one reason why it's going to be, and I mean, that's pretty far downfield. What's one reason? Well, I mean, less shielding is for both reasons, but I mean, how is it less shielded? What's one way that's less shielded? Because of the chlorines. And then the second way, which some people forget, is the fact that it's a hydrogen by itself. Okay, so whereas like a methyl group versus a methylene, a CH2 group versus a CH group. Okay, and so yeah, it's pushed further downfield than the methyl group. But then if you look and you see this methyl group, it's called a doublet because it gives off 2, like it's considered one peak or one signal, I should say, but it's been split into 2. Okay, because that's called a doublet. Then if you look at the CH, it's been split into 4, quartet. So we have singlets, doublets, triplets, quartets. I've heard some people say quintet, but some people say pentet for 5, and then hextet, and so on and so forth. So if you just didn't know anything else, this would look like how does 3 hydrogens give off 2 peaks, whereas 1 hydrogen gives off 4, splits into 4. There's something that, the way I learned it, it was called the J+1 rule. Some books may call it N+1. But the splitting in proton NMR, and this is only true for proton NMR, the splitting, let me just write it out, is J, what is the plus sign on this? +1. Oh, I forgot it's all in whites. Select all. Well, come on, let me select it. Well, there we go. J+1 rule. Come on now. This thing is not the easiest to maneuver. The J+1 rule tells you the multiplicity, or the way that it splits. So what J is the number of hydrogens on adjacent carbons. So let's put that down here. So if we look back at this example, and we see that the CH group, it only has one neighboring carbon. There are 3 hydrogens on it, so therefore the J rule would be equal to J, I should say, is equal to 3, so 3 + 1 becomes 4. And so that's the reason why it's split into a quartet. These simple quartets are roughly symmetrical, so it really does look, small, large, large, small. It has to do with, I forgot what that, for those who have studied a lot of math, there's the series where it goes like, oh, I'm trying to remember now what the series was called. Well, it slipped my mind, but it is due to the series, is it Pascal series? I can't remember now. That'll come to me later, most likely. And so you'll see the same type of series over again. So you can either have a single, a double, the triple, but it's got to be, the area under it's going to be symmetrical, and then the quartet and the area is going to be symmetrical under that curve. Okay. All right, so for simple cases, once again, it's equal to the number of equivalent. Vicinal is the scientific word for neighbor, okay, in here. When we say vicinal proton or vicinal carbon, it comes from the same term, from the vicinity. Whereas if it's on the same parent atom, does anyone know what it's called? Like if we're talking about the hydrogens and the methyl group, since those 3 are on the same parent atom, does anyone know what those are called? Instead of vicinal, they're called geminal, from Gemini twins, because they have the same parent. And so vicinal means you're on neighboring atoms. Gemini or geminal means that they come from the same atom. Okay, just in case you read that, because remember this, we actually go over those terms, I think in chapter 5 for alkenes first. And so you may, since this is chapter 12, they may use those terms out there, but vicinal means it's the neighboring one. Okay, so for simple cases, it's going to be equal to the neighboring carbon, the number of hydrogens on the neighboring carbon. All right, so here's another example. And if you have problems seeing it written this way, feel free to go ahead and draw it out whatever method works best for you. This is going to have 3 carbons. So it's got a methyl group attached to that CH group attached to a methyl group. And then there's a Br hanging off. That's the way it's drawn. So it may then be a little easier for some people to see it that way. And so if we look at the one that's closest to the Br is definitely going to be further downfield than the methyl ones. The methyls are going to be split to a doublet, and the reason why is both of these methyls, since they're equivalent, they have one carbon that's neighboring them, and it has one hydrogen. So J is equal to 1, 1 plus 1 is 2, so we get a doublet. Whereas if we look at the one that's hanging off of carbon number 2, it has 2 neighboring carbons. Each one has 3, so it's 6, and 6 plus 1 makes it 7, so it's a septet. Okay, and so you see like this Gaussian type of distribution there. But once again, you would actually, if you did the integration under this curve, which, let me do this. So if you did the integration under that function, that curve, it would be equal to 1, whereas the area under this would be equal to 6. So that's what it means by integration. All right, so I had already had some examples that had made out my notes, but it's not been a very good day. So first of all, I picked up the wrong quiz for biochemistry, and then I picked up the wrong set of notes for organic. So I'm batting 1,000 right now. Okay, so let's just together. First off, let's change this to black. Thank you. I don't know why the default is not to record whenever you do a new one. So let's... Whoops, that's supposed to be connected. It did not connect well, though. There we go. So I would expect you to be able to name this one, first off. 2-methylpentane. Okay. All right. And I will help you draw the axes, that kind of stuff. So once again, it's a delta. ppm are the units. We'll put in 0. There's the TMS for 0 to 10. This is a proton NMR. It is going to be coupled. Okay. Whoops. And now I'm going to give you guys at least 2 or 3 minutes to get started. Remember, the first question that you need to ask is how many different types of hydrogens there are, because it's going to tell you the number of peaks, number of signals. Then you go with integration, and then finally the splitting. Pause it while you guys are working on that, because otherwise I'm going to push record this time. Okay, so first off, how many different types of hydrogens are there? 5. There are 5. If you have a really good magnet, you're going to find out that there are 5. Okay, so first we have this one here. I'm going to just put on this end. Okay, and I'm going to call it A. Are there any others that are identical to A?
Far left.
Is the far left really? No, the far left is not. It's different. Okay? Because once again, if you substitute a chlorine for one of the hydrogens on the A, you'd come up with one name. If you substituted a chlorine on that one that's on the far left, you'd actually come up with a different name for the compound because it's not symmetrical. Before, and that's why I deliberately made this one, because it's not symmetrical compound. Before, pentane is symmetrical. Okay?
So that's how we would ultimately decide or see the different types of carbons.
Pardon?
By replacing it.
Right, yeah, that's the one way. Because if you replaced A, then it would be, 1-chloro-4-methyl pentane. Whereas if you replaced, one that I'll call, B, just because I'm already down there, and you replace it would actually be 1-chloro-2-methyl pentane. So see, the name is different. Okay. Now, so since I've already named this one B, are there any other carbons that have hydrogens that would be equivalent to B? Yes, this one, because they're hanging off the same parent. Those would be geminal methyl groups. Okay, so that one's a B as well. What about, I'll call this one, I won't use C just because of the fact that means carbon already. If I call this one D, are there any others just like D? No. Okay, then we have E, and are there any others that are identical to E? No. Not if you have a really good magnet, you'd be able to separate it out. And the reason why is, once again, if we replace a chlorine here, then we would have, three, it would be like 2-methyl, 3-chloro, 2-methylpentane. If you replace, I'm going to call this one F, because it just makes sense. And I lost my signal. But if you replaced one on the one that was on F, then it would become 2-chloro-4-methylpentane. So let's see. Good eye. All right. So there's A. Now we want to say which one most likely comes next. Most likely it's going to be B. Okay. Now there are going to be some, if you just use logic, there are going to be some that's going to be really hard to differentiate where they start to get closer and closer together. So that's why the stronger your magnet is, the better the resolution, the separation between the peaks. But using the logic here, we would say B. And B is going to integrate to how many hydrogens are in that B environment? 6. And so that's going to be B. And how many neighboring carbon or carbons does B have? Just 1. And how many hydrogens are on that one? 1. So 1 plus 1 is 2. And so we're going to have, and it would actually be something really big, because there we go. So we've already done B, and we've done A. What one most likely comes next? F. Okay? So F is going to be in this color. And how many, it will integrate to how many, because how many hydrogens are on it? 2. So I'm going to go ahead and just write that in up here. Okay, and now for the J, so skip ahead, the J plus 1 rule will end up with how many, splitting into how many peaks? 6. Because A has 3, E has 2, so that's 5, and 5 plus 1 is 6. 1, 2, 3, 4, 5, 6. So now we have, what one's going to come next, D or E, most likely? E, and I'll do it in this color. So we have E. And how many will it integrate to? How many hydrogens are in E environment? 2. Now, for the J plus 1 rule for it, how many will it split apart into? 4. Because D has 1 hydrogen. I've already lost my letters. F has 2, which is 3, and then 3 plus 1 is 4. 1, 2, 3, 4. And last but not least, we have D, which I'll put in that color. So there's a D, and it's going to integrate to what? 1. Now, how many will it split into? So we have 3 plus 3 plus 2, correct? 3 for the B's. That's 6. 2 be 7, 8, and so 1 would be 9. So it's going to be I think that's called a non-net, I think that's what it's called. That's when you definitely would write down below, okay, there are 9 peaks, because it's going to be really tiny. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so that's what I would expect you to be able to do at this point. Now, what about alcohols and carboxylic acids, for that matter? They both have hydrogens. The rule of thumb is, if you have a good magnet, their hydrogens do not split. Okay? They don't. They always come up as a singlet for any decent NMR. And the reason why is because those hydrogens are constantly popping off doing what's called solvent exchange. They pop off and they exchange with the water or the other alcohols around or anything like that. We've already seen that when we were doing pushing before. You'd seen what the alcohol or the water would go and grab a hydrogen and it would lose a hydrogen. It just constantly does it. So it doesn't stick around long enough for it to split because it leaves. I hate saying it splits, but it takes it hits the door. And especially carboxylic acids, the pH, because those are acidic hydrogens, so they pop off all the time. Okay, so that's one thing. And secondly, they don't get included usually in the J+1 rule. If you have a decent magnet, because they're not around long enough for them to be included in J+1. That technically they're not a carbon. But so that's why alcohols are different. Usually, alcohols also can really fluctuate where they show up on the NMR. Sometimes they're, whoa, didn't mean to do that. Sometimes they are more down this area, sometimes they're more here. Usually carboxylic acids are pretty far down. So I just wanted to give that heads up. Usually when I draw them and you will draw them, we'll put them far downfield just because it makes sense, and many times they really are around 6 or 7. But I just want to let you know, whenever we start doing this in the lab, don't be alarmed if your alcohol peak is at 4, just because it's not, since it's exchanging so quickly, it doesn't always follow the rule. Okay, so we have 5 or 6 minutes left. I want to do something that I haven't checked the most recent edition of your book, but in the earlier editions it did not have this. Okay, and so it's my little, it's not cheating because it's an equation that you will need to memorize. But we're now going to learn how to go from the NMR structure to drawing the compound. We're going to work backwards. Okay, but the problem is how do you know if there are any rings or double bonds? Like so far we're just doing everything with single bonds. But what happens if it's a ring structure or if it has double bonds? It's toying with me. It's trying to say that I need more patience. Okay, so I'm going to give you this equation. I learned it, and they called it the ring double bond equation. I know yes, thank you. I know that my organic 1 professor was not the most creative, but that's what he called it. Equation. I just call it EQN. Okay. And I'll tell you right now that I will not UN, EQN. Thank you. All right, and I will call it the RDB from now on, not to be confused with RGB. RDB. Okay, for rings and double bonds. And so what I mean by that is this is the formula. It's equal to 2 plus, let me write it out. This is a Roman numeral 4, in case it doesn't come through very well. Okay. And this is one that looks odd, but it will be a lifesaver for you. You just need to memorize it. It's 2 plus 2 times 4 plus 3 minus 1, and all that's divided by 2. And so the 4, it equals tetravalent atoms, which for organic chemistry, whoops, this is not wanting to. What in the world happened there? Undo. No. Huh. Interesting. All right. So RDB is equal to 2 plus 2 times 4 plus 3 minus 1 divided by 2. Okay. So the 4 is equal to tetravalent. I'm not going to write that one out since I'm having a problem. Which for us is carbon. Carbon. the number of carbons that you have. I guess in theory it would also work for silicon, but you know, how often do you work with silicon? So 3 are for the trivalent atoms, which they make how many bonds is a trivalent atom going to make? 3. And so the example that we use the most of this is going to be nitrogen, because nitrogen likes to make 3 bonds. 1 are the monovalent or univalent atoms. So how many bonds do they like to make? 1. So what's one atom or one element that likes to make and can only make 1 bond? Hydrogen is the biggie. And then what else can only make 1 bond? The halogens. And so I'm just going to put that as an X. And so whenever you're given the spectrum, you're going to be also given the chemical formula. Use the chemical formula in the RDB very first thing. That's the rule of thumb. Just do that first. It will make your life much, much more simple. So, one example, and this will be where I end, and then we'll on now. Got it that time. So, the example that we're going to do first, this is going to be C8H10 oxygen. And we're going to say that the IR shows no alcohol. So you do the IR on this first, just like what we did in lab, and it didn't have that big, dip in it. So that's, okay, we know it doesn't have an alcohol in it, but we know that that's the chemical formula. And this is what the spectrum looks like. Chances are I'm going to have to ask somebody to let me know which one I drew, because I have multiple of these. Okay. And the number above it is going to be the integration. Okay, and so that would be the NMR that I gave you, the proton NMR, and I gave you the information of a C8H10O, so it has 1 oxygen. The IR has no hydroxyl groups, and on Friday we'll go over what does that mean? How do we put the pieces together? How do we go from this to know what the structure looks like? And we will do lots of examples. Have fun with these. Some people really like these because they're little jigsaw puzzles. Okay, so I'm going to go ahead and end class with prayer.